Professor Maissam Barkeshli. We will talk about crystalline gauge fields and quantized discrete geometric response theory for topological orders with spatial symmetries. Maissam, you can begin sharing.
Okay. All right, so thank you for the invitation to speak. I'm going to be talking about some work that I've been doing with my student, Tanar and Manjunath. And most of what I'm going to be telling you is in a paper that we posted to the archive a few months ago. And there's also some ongoing work that we're doing along the same lines. Okay, so the question that we're trying to address is we want to develop an understanding of basically how to get a complete set of topological invariants for gapped quantum states of matter. We want to understand what physical phenomena these imply, and then we want to understand how we can extract these invariants in experiments and in numerical simulations. And even though there's been a lot of work in this direction for the last 40 years, there's still, I think, some basic questions that we actually don't really know how to answer. Now, in 1+1D, this problem has basically been solved by the theory of symmetry-protected topological states, or if you like, invertible topological phases, basically, in the last 10 years. And so what I'm going to do in this talk is I'm going to focus on 2+1D systems, and I'm going to be interested in bosonic topological phases. So when you think about topological phases in 2+1D, so we all know that the way to think about the problem is first we forget about the symmetry, then we have the intrinsic topological order. And we believe that the intrinsic topological order is fully characterized by two objects. One is what's called a unitary modular tensor category, more colloquially known as the algebraic theory of anyons. And this is the mathematical theory that characterizes the braiding and fusion data of the anyons. And in this theory, there's a set of data and gauge transformations of that data. So the gauge invariant combinations of that data are what correspond to the physical topological invariants that you can hope to see in numerical simulations or even experiments. So these include, for example, the topology-dependent ground state degeneracies, modular S&T matrices, topological entanglement entropy, and many other issues that people have been talking about for over 30, 40 years. And then the other thing is the chiral central charge of the edge theory. Now for bosonic systems, the modular tensor category determines this chiral central charge mod 8. So all you need to know is what's beyond the mod 8. Now, when you add symmetry, then you can get additional symmetry-protected topological invariants. And when you have a system that has intrinsic topological order together with symmetry, we call that a symmetry-enriched topological state. So some famous examples of symmetry-protected topological invariants would be the quantized Hall conductivity or the Chern number when you have U1 charge conservation, the fractional electric charge of quasiparticles. What's maybe slightly less famous is if you have continuous rotational and translational symmetry, you can define what's called the shift of fractional quantum Hall states. It's basically the shift in the relation between the filling fraction, between the number of particles and the number of flux through a closed surface. And that's closely related to the quantized Hall viscosity. And similarly, anyons can carry fractional quantum numbers like a fractional orbital angular momentum. And this is packaged in what's called the spin vector that was originally discussed by Xiaogang in the early 90s. So the question that we'd like to answer is, what is the full set of symmetry-protected topological invariants when you have U1 charge conservation symmetry, and then you have some kind of space group symmetry on the lattice, for example. And the particular kinds of space group symmetries we're going to be interested in are discrete translation symmetry and then some point group rotation symmetry. So this would be the orientation preserving space group symmetries for 2D lattices. And I think that this question is particularly relevant these days. For example, in the last few years, Andrea Young's group discovered fractional Chern insulators in experiments. So those are situations where you have some kind of fractional quantum Hall type state, but it's happening in the presence of some periodic potential. And then you have these topological phases where the lattice symmetry is, or at least the periodic potential is playing a crucial role. So you could ask, well, we'd like to know what are all of the possible topological invariants that this system could have, and then set about trying to figure out how you might measure them. Now, the group that I wrote is U1 cross G space. We can also consider adding a magnetic field. Then translations in the two directions don't commute with each other. So really your group is a central extension of the space group by U1, where the central extension is parameterized by the flux per unit cell. So we've been using this kind of weird notation that I saw in Xiaogang's paper. I don't know if this is standard at all in math. Okay, so just from a high level, when we want to think about how you describe SETs, well, one of the understanding over the last few years has been that the very comprehensive mathematical framework for describing SETs is what's called G-crossed braided tensor category. And the idea here is that now you have some algebraic rules that characterize the fusion and braiding properties of the symmetry defects together with the anyons. And then the gauge invariant data of this mathematical structure gives you the symmetry-protected topological invariants. So just very briefly, this theory has kind of three main steps to consider. The first step is you ask how symmetries permute the anyons. So that's described by this group homomorphism rho from the symmetry group G into sort of the automorphisms of the modular tensor category that describes the anyons. Then you can talk about symmetry fractionalization. That dictates how the anyons carry fractional quantum numbers of the symmetry group. And this forms what's called a torsor over the second cohomology, where the coefficients here is A, which is the group of abelian anyons in the theory. And these days, if you're a field theorist, you would call A the group of one-form symmetries. And the final layer is, once you've understood how the anyons carry fractional symmetry quantum numbers, then you start to develop a theory of the braiding and sort of fusion data, the F symbols of the symmetry defects. And it turns out that this forms a torsor over the third cohomology group. So the torsor aspect here just means that different SETs would be related to each other by stacking an element of this H3GU1, which physically corresponds to stacking SPT states in 2+1 dimensions. And there are various obstructions that come into this story. And actually recently we understood how to calculate these obstructions in basically complete generality in a paper posted a few months ago. But anyway, in this talk, I'm going to assume that we have no permutations. And it turns out that in our examples, all these obstructions always vanish, so we don't have to worry about them. Okay, so what I want to do is I want to develop some understanding of the case where my symmetry contains not only some on-site symmetry like charge conservation, but also contains like a space group symmetry. And we expect that this G-crossed braided tensor category framework can be used both for on-site symmetries and also if we have spatial symmetries like translation or rotation. We don't have a proof, this is kind of like a conjecture. But this is consistent with everything that we've seen in quantum field theory of many-body systems, which is that whenever you have a spatial symmetry in some microscopic lattice model, that manifests in the effective quantum field theory description as some internal symmetry in the quantum field theory together with some spatial symmetry of the quantum field theory, like a translation or rotation within the quantum field theory. Recently, this kind of conjecture has been referred to as the crystalline equivalence principle. And it turns out that it's been tested rather extensively for SPT states, which are just topological phases which have no intrinsic topological order. So this gives us even more confidence that this is basically the right thing to do. So I have some additional words here about what I kind of mean about this statement more precisely, but it doesn't really matter. So I'm going to skip it unless someone asks me about it. Now, what I discussed so far is kind of a high-level description in the sense that it's very general. And it can apply to the G-cross braided tensor category theory can be used, for abelian phases, non-abelian phases, all kinds of symmetry groups which are unitary and preserve the orientation of space. But if you kind of focus the discussion on some simpler situations, like abelian topological phases where symmetries do not permute the anyons, then actually, in some sense, it's more convenient to just use what we're more familiar with in physics, which is some effective action. Now, when we talk about, say, fractional quantum Hall states, abelian fractional quantum Hall states in the continuum, the effective actions have been studied for a very long time. And when you take into account the spatial symmetry, then you also have a coupling of the theory to basically to gravity. So here, this first term would be the usual K matrix for the abelian Chern-Simons theory. And then we have some additional terms where capital A is the background U1 gauge field and omega is the spin connection. And here it's just the spin connection of the space that the system lives in. So it's just basically an SO2 gauge field, or effectively U1 gauge field. And so this Q is the famous charge vector that everyone knows. S is the spin vector that I mentioned previously, which was introduced by Wen and Z. And then you can have these additional terms as well. So now we're going to go and try to think about what would happen on a lattice. And so what we're going to do is we're going to introduce background gauge fields associated with the lattice symmetry and the U1 symmetry. So we're going to introduce background gauge fields for the full symmetry group G, which is this U1, and then we have the Z squared component for lattice translation symmetries, and that's and then we have the lattice rotation piece over here. And the way that, because these are discrete symmetries, it's most natural actually to take our space-time, which is just space cross time, and we're going to pick just some triangulation of M. And because we're interested in topological terms and topological field theory here, everything's going to be independent of the actual triangulation that we pick. So we're just going to pick some arbitrary triangulation of M. And then on links of this triangulation, we have our gauge fields. So capital A will be the U1 gauge field. Capital R, which is a vector, is going to be the translation gauge field, and it has two components, the X and Y components. So X is a Z gauge field and Y is a Z gauge field. And then we have C, which is the discrete rotation gauge field. And if you look carefully here, what I've actually done is A is actually the lift of the U1 gauge field to the reals, and C is actually the lift of the ZM gauge field to Z. And we need to make sure that whatever action we write down is independent of the lift. Now, gauge transformations, then you can kind of just read off from the group multiplication of this group. So we do gauge transformations for the translation and the rotation, that's R and H, and then we get this kind of gauge transformation. So one thing that's going to show up repeatedly in this talk is this U of C. So U of C is the representation of this group elements as a 2x2 matrix. So if this is some Cij here describes some rotation by some angle, and U of that is just the 2x2 matrix corresponding to that. And in particular, we're always going to be working in the basis of where the lattice vectors are the two components of the basis. So just what does this actually mean if we have this crystalline gauge field? Well, the one way to think about it is, here's an example, is let's say that we have these vertices around a hexagon, and we label our vertices 0, 1, 2, 3, 4, 5. The translation gauge field is basically kind of the gauge ambiguity is basically an ambiguity in how we decide that we're going to label the positions over here. So in this configuration, the translation gauge field is all 1, 1, 1, 1, 1. And here I've picked a different gauge configuration. And now my labels for the vertices have changed. So basically, this translation gauge field is just a way to keep track of the difference in coordinates between the points I and J. The rotation gauge field is just something that lets us keep track of the relative orientation of the coordinate axes between points I and J. So if red labels some particular orientation, this red vector, like say the x direction, then if the gauge field is pi over 2 on some link, then that local orientation changes by pi over 2 rotation. And that's the gauge transformations. So, if you've done any geometry, this should look very familiar to you. These are just discrete analogs of the famous coframe field and spin connection, which is used in continuum geometry. But importantly, I'm not working with the coframe field and spin connection directly. I'm using this discrete analog, and this is important because the gauge transformations are now discrete, and this discreteness of the gauge transformations actually affects the analysis of topological terms. So kind of in the last decade, there were a lot of people who were trying to study, the crystalline response of topological phases and so on. And then they took some low energy field theory, coupled it to E and omega, and then tried to develop an effective field theory. But those analyses kind of missed some of the important physics about topological invariants because they didn't really completely take into account how really now we have these discrete gauge transformations. Okay, so this kind of looks unfamiliar. When I was thinking about this stuff, I certainly had never really seen it before. But it turns out that to some extent, these are actually well-known things in the theory of elasticity. In particular, like if you look at this massive book by Kleinert called Gauge Fields in Condensed Matter in volume 3, page 1000 something, he discusses how you naturally have translation gauge fields when you try to do elasticity theory. Because when you talk about the displacement field in elasticity theory, that necessarily has some intrinsic ambiguity, which is due to relabeling of the atoms. Basically, you can change what you call, where you say each atom is kind of, you can just relabel every atom, and you're still describing the same exact situation. So Kleinert says, well, this means that our elasticity theory should actually be invariant under this gauge transformation, which is you change the displacement vector of an atom whose mean position is R by some integer multiple of the lattice spacing. And this means that when you do elasticity theory, the distortion tensor, this diuj, should actually be coupled to a gauge field. I mean, there should be some kind of minimal coupling. So you replace this diuj by diuj together with some translation gauge field. But it turns out that I haven't seen any discussion in elasticity theory where people take into account both the rotation gauge field and the translation gauge field and kind of are very careful about the group structure which relates rotations and translations, the non-abelian group structure. So I actually haven't seen it discussed completely in elasticity theory, but that's part of what we're going to try to do. And I should say recently crystalline gauge fields have also appeared in some discussions of topological phases of matter or ultra quantum matter. And in particular, these two papers have some nice discussions and applications of some crystalline gauge fields. Although the full-blown crystalline gauge theory in 2+1 dimensions, which I'm going to describe here, I don't think anyone's really done. Okay, so at some level, all this crystalline gauge theory is doing is it's basically a way of encoding all the physical properties of a lattice, the positions of the dislocations, disclinations, the lengths and areas. These are actually the physical properties of a lattice. So the flux of this discrete gauge field C gives us the disclination angle. When C is 0 everywhere, the holonomy of R, the translation gauge field, gives us the Berger's vector of the dislocations that's inside the loop gamma. And if we're on a torus, then we can integrate the gauge field over non-contractible cycles, x and y. So that would give us like the length in the x direction, length in the y direction, and then the shears in the two directions. But when C is non-zero, the story gets more complicated, because now you have a local change of the coordinate frame along gamma. So if you wanted to describe the Berger's vector.
Can you step back a little bit?
Yes.
When are you on the lattice and where are you in the continuum?
I'm imagining that I have a continuum theory, which I've basically triangulated the spacetime. And the configuration of the gauge fields is telling me where, you know, dislocations and disclinations are.
You're doing a continuum field theory.
I'm doing a continuum field theory, which has been discretized because I have discrete gauge fields. But I have forgotten about the lattice completely, except for the data of these R and C gauge fields.
So in what sense do you have the translation group is Z or Z squared rather than R squared?
Well, I'm remembering the fact that the symmetry was Z or Z squared. And
the lattice spacing was already set to 0. So what sets the spacing in the Z?
well, for example, I can only have disclinations with a quantized angle, 2 pi over m. Even
I am not confused about the rotation. The rotation I can understand. I'm confused about the
it's the same thing with translation, right? The dislocation, the Berger's vector of the dislocation is quantized. So in the continuum geometry, dislocations corresponds to torsion. But I need to remember the fact that, you know, the Berger's vector of dislocations is quantized. And it can't be anything that I want it to be.
It comes down to this crystalline equivalence principle in some sense. Like, you don't need the symmetry to really be a spatial symmetry at this point, right? It's just some symmetry. It doesn't actually need to act on space. It's some discrete symmetry of the problem, right?
Yeah, I mean, effectively, I'm treating the symmetry as an internal symmetry at this point. Once I've gone to the continuum theory, it's effectively internal symmetry of the field theory, but I need to.
It has nothing to do with your geometry.
No, but I need to remember what the I want to remember what the physical meaning of the fluxes are. Right? I want to remember that when I have some flux of this translation gauge field, I want to know what it means.
So, for example, if you put some metric on that space, how will things change? Will it depend? Will you need to know that the two are related or not?
Yes, yes. You need to match the metric and the spin. You need to match the metric of that continuum space to the properties of these gauge fields.
So this is not an ordinary gauge theory because it also couples to the metric in a different way.
That's right, but I guess I'm forgetting. I'm not including a metric explicitly anywhere. But so in a way, this R and C are keeping track of the only way in which I'm going to add any kind of geometry to the system. I'm not going to consider some independent metric. Well, yeah, I mean, R and C already describe everything I want to describe about the geometry of the space. There's really nothing else that I'm going to add. Because if I have a lattice, there's no real notion of anything else aside from lengths and area. Well, yeah, I mean, I'll get to it, but the translation gauge field is also going to specify what the local area is for me.
So the thing I'm puzzled by is is your theory topological in the end of the day or not?
The theory is it depends what you mean by topological, but yes, it is topological in the sense that it's going to be retriangulation invariants, and it's going to be independent of all of these of any gauge transformation. But because R and C carry information about the geometry of the lattice, it depends what you mean by topological invariance. Like I think the best thing to do here is just think about this R and C as internal gauge fields and just try to think about what the physical meaning is of their fluxes. Okay. So when C is non-zero, then it's more non-trivial to think about the Burgers vector, because you have this local change of coordinate frame along the cycle gamma. So what you need to do is you need to do some notion of parallel transport. You need to pick some origin, 0, and then you need to pick a path from 0 to the point k, and then you can define a parallel translated version of this r k k plus 1 defined by this equation. And now if you calculate the loop integral of this script r around gamma, that gives the total Burgers vector of dislocations in gamma. But this isn't fully gauge invariant because we still had to pick a coordinate frame defined at that origin 0, right? So this is the Burgers vector in the coordinate frame defined at the origin 0. Okay, so let's think about we want to write down an effective action, so we have to think about what kinds of symmetry fluxes we can write down. So there's obviously the electromagnetic flux, there's the disclinations. Now the new things are we have this area element, which is basically the cross product between, if we have some 2 simplex ijk, then the area element is defined by this cross product over here. And then, so that's no problem, but you can ask, what about the dislocations? Dislocations, it turns out, are pretty non-trivial to think about. Because dr is not gauge invariant when I have this non-zero C. D script r, which I just defined for you, is non-local because it depends on this origin 0 and a path from 0 to wherever I'm calculating this flux. And furthermore, it's still not fully gauge invariant because it depends on the coordinate frame at the origin. Okay, so just the naive things actually don't work. You need to think a little harder. And physically, what this means is that, if I want to define a Burgers vector for some region D, we need to pick some choice of coordinate frame at some origin 0. So if I ask what's the total Burgers vector of some region that contains 2 subregions D and D prime, well, that's going to be ambiguous up to independent local rotations of the coordinate axes defined at 0 and 0 prime. Now, we can get around this problem by always picking a common origin 0 for all possible regions, but then the notion of this Burgers vector is not completely local. So we won't have a fully local notion of gauge flux. And even then, it still changes under a local rotation at this origin 0. So it's not fully gauge invariant either. But it turns out, so here's the interesting thing, it turns out that if you do take into account these local rotations, there is a finite group grading on Burgers vectors, which is k sub m. And it turns out this finite group grading can be used to get a fully local and gauge invariant notion of a translation symmetry flux. So let me show you the picture of how that works. So let's consider n is 2, so we have 2-fold rotation symmetry. We're on a rectangular lattice. And I have some region where the Burgers vector is pointing along the x direction. Well, I can do a local pi rotation, so that flips the Burgers vector over into the other direction. And then similarly for the Burgers vector in the y direction. So we have these equivalences. However, if I have 2 of them, well, 2 of them, because I can do a local rotation, is equivalent to this one, which is no Burgers vector in total. And similarly here, if I do a local rotation on the right side, that's equivalent to this. I think this is a typo, it should be 0, 0, I think. So anyway, so now we see that there actually is a finite group grading of Z2 squared because the Burgers vector, modulo this equivalence will still be well defined. For m equals 3, there's a similar story. We have these local rotations. And if I have 3, the Burgers vector 3 comma 0, if I do these local rotations, that can be trivialized completely. So for 3-fold rotations, I have this grading Z3. And then you can go through the analysis for 4 and 6 as well. So mathematically, what's happening here is one can show that this Rij that I defined is related to the parallel transported, the correct Rij, if you take into account parallel transport from 0, by an integer vector times this 1 minus u of 2 pi over m. Remember here, this was the 2 by 2 matrix representation of the 2 pi over m relation. And it turns out that from this, you can prove that this quantity is actually completely gauge invariant up to an integer vector. So the fractional part of this quantity is actually fully local and gauge invariant. So that motivates us to define what we call R slash, which is just this 1 minus u of 2 pi over m inverse times R. And then, if we take the holonomy of that, mod 1, this quantity is always gauge invariant. And so the gauge invariant local translation symmetry gauge flux is actually this 1 over 2 pi d R slash mod integers. Yes? Yeah,
can I ask a quick question?
Yeah.
I just want to understand this in a simpler language, if I can. So are you describing a general phenomenon when the gauge field are non-abelian? Like, I mean, holonomies are still subject to conjugation at the origin. So it's not like truly gauge invariant.
Yeah, I mean,
so essentially, you're elaborating how this works for the specific group Z2 cross Z2 semi-direct, whatever rotation that you're
Z exactly. Z squared semi-direct rotation.
Okay, thank you.
Mm-hmm. So this quantity defines this finite group grading Km. And so the groups here are what I've shown in this table on the right-hand side. So for 2- and 3-fold rotations, we already went through it with those pictures. For 4-fold rotations, Z2. And then for 6-fold rotation, it turns out this group is completely trivial.
Sorry,
Yes.
Mason, to go back to Chao Ming's question. I mean, are you describing the conjugacy classes of the group, or?
The conjugacy classes.
Because usually for a non-abelian group, you label fluxes by conjugacy classes, right?
But that's when when you gauge it, then you label fluxes by conjugacy classes. But like when we do G cross, we don't, when we talk about symmetry defects, we don't necessarily, we're not always forced into that. But yeah, I think you're right. Yeah, these are just basically conjugacy classes, I think.
But conjugacy classes don't form a group.
Yeah, because
okay, well, then I need to think about, in this case, we do have a group. So I need to think about the relation to conjugacy classes. Maybe in this particular case they do, but I'm not sure. In this case, we get this, in this case, we do get this group. But I'll think about that. Okay, so now what we're going to do is, now that we understand all the fluxes, then we're going to try to write down an effective action. So here we're doing everything in this simplicial complex. So we're using this cup product. So if I have a 3-simplex IJKL, this is the definition of the cup product. So we have the symmetry fractionalization, and then we have these SPT terms over here, which are also called Dicraft-Witten terms. So the symmetry fractionalization piece has 4 quantities over here, and that's related to the fact that this H2 of GA, it turns out is given by this group. So the only thing that's kind of new here is this Km tensor A. So if you think, if the tensor product here, if you have ZP tensor is ZQ, then this group is just Z of the greatest common divisor of P and Q. And then for more complicated abelian groups, and this is sort of just kind of a generalization of that. For the SPT terms, these are also called Dicraft-Witten terms for the background gauge field. We have basically 7 of them, and that corresponds to the fact that this H3GU1 has all these different pieces. So we have ADA and A cup AXY, that's this integer, the 2 integers K1, K6, and K2, K3, and K7 are valued in ZM, and then we have this Km squared. So that's these vectors, K3, 4, and K5. So I'm going to go through what these physically mean. And in this theory, the gauge fields must be flat for the action to be completely well-defined. In other words, for it to be independent of the lift to R and Z that I mentioned earlier. So if you want to describe non-trivial fluxes, the way that to do it in this theory is that you have to put in punctures and then have non-trivial holonomies around those. So let's talk about the symmetry fractionalization first. Yes.
Sorry, AXY, is it like just X cup Y, where X and Y are the two translation?
It is X cup Y if C is 0. If C is non-zero, it's a little bit more complicated. It's basically, I wrote the formula here. It's basically this. So when C is 0, this is just basically X cup Y. But you need to take into account this rotation as well. Okay. Okay, so the first piece, the charge vector, everyone knows about it. I'm not going to say anything. S is the spin vector, but here we have a discrete version of it. Again, basically everyone knows about it. Just say a few words. Physically, what S means is that if you fuse M elementary 2 pi over M disclinations together, that leaves behind an anion S. And furthermore, if you have an anion labeled by the integer vector L, then you have a fractional orbital angular momentum, which this piece gives a contribution of L transpose K inverse S. And importantly, we have an additional equivalence here, which is a little bit non-trivial and maybe somewhat surprising to some people, which is not only do we have this first equivalence, we have this second equivalence. And what this means is that if S were just M times an integer vector, it would actually be should be viewed as trivial. And that's because you can account for it completely by local energetics. You can always just bind the elementary disclination to your anion lambda by some local energetics. And then you can completely account for this kind of a term if it were of this form. So we actually need to mod out by this kind of equivalence, which is why we have this one over here. And that gives us A mod MA in the symmetry fractionalization over here. So the third thing, this is what seems to be new. I haven't seen it really discussed anywhere, is what I would call the discrete torsion vector. So this thing has not only does it have no analog in the continuum, it is only non-trivial when this Km is non-trivial, which means it's only non-trivial for 2, 3, and 4-fold rotation symmetry. And what this term does is that it associates an anion, so this anion where A and B are integers, to a region which has trivial Burger's vector according to the group grading, Km, which means to a region whose Burger's vector is of this form. And furthermore, this is kind of the analog of, in the previous case where we had the anion S when we fused M 2 pi over M disclinations. This is kind of the analog of that. So this thing gives rise to a fractional linear momentum of the anions, given by this kind of formula for the anion L. And similarly to the case with rotations, this T is trivial if it can be completely accounted for by binding anions to elementary dislocations. So that's why you wind up with this funny group over here. The fourth thing, the fourth term M has been discussed before. This also has no analog in the continuum, but it's basically the fact that you can have an anion M per unit cell. And this leads to the fractionalization of the translation algebra, which the discussion of this goes back a long time, at least to the early 90s by Sachdev and others, and maybe even before that, I'm not sure. And this is what's called crystal momentum fractionalization sometimes, like Essen and Hermeli called this crystal momentum fractionalization. This number 3 over here is kind of a different type of crystal momentum fractionalization that we usually don't talk about. Okay, so now.
Sorry, Maissam, you
Yes.
need to wrap up soon.
Okay, I'll just give me can I have 2 minutes?
Sure.
Okay, so now what we can do is we can do the usual approach, integrate out the internal gauge fields, get a response theory, and now we get all kinds of response terms. Only 3 of them are discrete analogs of what we have in the continuum, these first 3. Everything else is basically totally new at some level. I mean, people have discussed aspects of it in the past, but I'm saying it is new in the sense of it's not a discrete version of what we get in the continuum. So 2 is this discrete shift. It attaches charge to disclinations and corners. It attaches angular momentum to 2 pi flux of A. So this term can define something that you might call a fractional higher order topological phase. The third term gives you a fractional angular momentum for a disclination. One thing that I think is quite interesting is this fourth term, which is a quantized charge polarization. So these guys, Chong, Ashvin, and others, last year talked about how polarization can be thought of as a non-quantized topological response. I think Ashvin called this the ultra-quantum notion of theory of polarization. But here we have a quantized charge polarization, and that's happening because of the rotation symmetry. So this fourth term over here is non-trivial only for 2, 3, and 4-fold rotation symmetry. And it's a polarization, meaning that you can see just from the form that it's going to attach charge to dislocations. It's going to attach momentum to the 2 pi instanton. And it's going to, if you define your system on a space with boundary, it's going to define some fractional charge per unit length given by this formula. The fifth term is the angular momentum version of this. And I think this is quite intriguing. It gives an angular momentum to a dislocation, quantized again. I don't really know how to measure this because I don't know how to move dislocations and disclinations. And I'm not even sure if the other properties, like the analog of momentum of an instanton or the analog of polarization on a space with boundary even make sense here. So I think these are interesting questions to think about. Then we have charge per unit cell, angular momentum per unit cell, and we have something new here, which is the linear momentum per unit cell, which is kind of interesting. I haven't seen that before. And then finally, we have a linear momentum of the dislocation. This kind of a term, which is this RDR term, sort of showed up in some earlier works, and some people call it the torsional Hall viscosity, but in previous works, it was never quantized. But here we're finding that it is quantized if you are careful about the discrete gauge transformations involved. But not only that, it's only non-trivial, again, for 2, 3, and 4-fold rotation symmetry. It doesn't exist in the other cases. So I'll wrap up there because I'm out of time. There's another way of understanding this finite group grading by thinking about polarization. And then there's a question of the classification, which is not just H2, H3. It's actually less than that because you can have certain relabelings. There's a continuum formulation, and I'll just end there. Okay, so I'll just end with a slide on future work. So thank you very much.
Yeah, thank you for a very nice talk. We already have many questions during the talk, so let's just take 2 more short questions.
Actually, I have a question.
Yeah.
So this may be a little bit vague, but we know that if we end up having a chiral phase, then the TQFT description, at least maybe Translaiman's description, would end up having framing anomaly.
Yes.
And is there some reflection of that in here? Because you do talk about rotation, which is kind of accessing the frame, but not in a 3D space-time sense. Is there some non-trivial constraint coming from that?
That's a very good question. So there's 2 issues about that. One is when you have the Lagrangian, we also have this additional term, this gravitational Chern-Simons term, whose coefficient depends on central charge, and we still have that in the discrete case.
Right.
So every time we talk about angular momentum of disclinations and stuff like that, there's going to be there's going to be an additional contribution from the central charge. So that's one thing. And then another thing is when we talk about the orbital angular momentum of the quasiparticle L, we get this contribution, but there should be an additional contribution coming from the topological twist. So if I were to transport an anion L around a disclination, I should expect a phase coming from this term over here, in addition to the phase just associated with the topological spin, which would be like L transpose K inverse L. So indeed, one would expect that.
So you're saying that the effect coming from the framing anomaly and the effect from this topological term coming from H upper 3 is essentially decoupled, and they just add.
They just add, yeah, that's right. And in fact, people have studied the analogous case in the continuum, and that's what they find. So like, there's a really nice paper by Andrei Gromov, where in the continuum, he does the adiabatic transport of an anion around a source of curvature, and he finds how, he does the explicit calculation, and he shows that there's like two contributions, one from this kind of orbital angular momentum coming from the spin vector, and then another contribution coming from the topological twist. So I'm essentially conjecturing that the same thing will happen in the discrete case, but of course, explicit calculations are harder in the discrete case because we don't have these nice holomorphic wave functions.
Thank you.
If I may?
Yes.
Yeah, so stay in this like this. So I'm still confused about what's topological and what's not and where the metric is. Okay. Normally, the statement is that if I just look at your Lagrangian, the first two terms appear topological.
Yeah.
But at the quantum level, we have to be more careful, and there's a framing anomaly and so forth. And this is captured by the last term in this equation.
Right.
What is the analogous statement here? So what's the relation between the omega, d omega, and L grav? How many metrics do we have here?
So we still have one metric. I think one way of saying it is that if I wanted to calculate the holonomy of omega around any cycle, it has to be quantized to this 2 pi over m. Right? So I have, for example, this kind of a constraint on the spin connection.
But I don't understand what's the input and what's the output. In other words, in the topological field theory, you take the first two terms in this equation,
yeah,
and you add the gravitational term as a consequence of the anomaly. And it's kind of similar to it's similar to the first term in the second row, which is some kind of a term that depends only on classical fields.
Mm-hmm.
That's not what you're doing. If I understand correctly, your omega is, your big A is classical, but your omega is dynamical.
No, big A and omega are always classical for me.
Okay, so I'll flip my question. So the dynamical fields are only little a.
Yes.
Good. So omega is associated in some way with the metric and the spin connection. And in addition, I thought you said that there's another spin connection that L grav is a function of.
Well, formally, we can think of L grav as a function of some different spin connection, because all I'm really doing, where'd it go? All I'm really doing is I'm treating the spin connection as an internal gauge field, effectively. So formally, I think it's completely fine to have the gravitational Chern-Simons term depend on a different spin connection. But that would be unphysical. Like that would not describe the physical lattice model in any way. The only time it would describe the physical lattice model is if we identified those two spin connections. So I identify this internal gauge field as describing the geometry of the system. I don't know if that addresses your question.
So omega is classical? I can't keep track of it. Omega, you say, is classical.
Everything is classical except for little a.
So why can't I just think of it as an ordinary abelian Chern-Simons theory coupled to various background fields?
It is. It is, but the point is that if I have discrete symmetries, I want to couple it to discrete fields. And I also want to be careful about what the meaning of these omega and its discrete counterpart is. And when I try to do that, I decide that I need to actually think of omega as the actual spin connection of the describing the geometry of the system.
What group is it of omega?
So in this continuum case, omega is just the spin connection, which is just basically SO2 gauge field in this continuum case. In my later theory, I have C in place of omega, and C is ZM gauge field. It's just the Z mod M subgroup of SO2.
I see.
Hey Maissam?
Yeah.
Can I ask about to what extent we know microscopic systems that realize non-zero values of all of your coefficients?
That's a good question. So it's almost trivial to have non-zero values of Q and S and M. We have those, and I do not know of examples of this T, because I don't even know what T is for any lattice model that anyone's ever studied, because no one's tried to even calculate it or talk about it. So for me, T is the big question here. I don't know. I mean, I suspect that for most models, people talk about T is 0, but there's like some variations on it that would make T non-zero, but I don't know of them. And then for the SPT terms, like the Ks, again, I think that the last like 2 or 3 terms here, I don't really know of lattice models, but the first 3 terms even show up, I think, when you study like the Hofstadter model at weak field, because these are just discrete versions of what we already have in the continuum. So if you study the Hofstadter model with very, very small flux per plaquette, you will certainly have, you can have these K1, K2, K3 type terms.
If we believe that we have constructions for any SCT with internal symmetry, I think you can, in principle, use that to construct anything you want with spatial symmetries as well.
Yeah, but I mean, those are, I agree with you, but those you may not think of as like, it'd be nice to have like something that's not like, oh, I have some like domain wall defect construction where, I create a lattice on top of something which already had a small lattice. But I agree, from that perspective, we can certainly construct probably anything here.
Yeah.
Yeah, okay, let me say the concluding words first, so some people can leave and others can continue with the discussions later. Thanks everyone for joining us. This is the last session for the summer seminar series, and the plan for the fall hasn't been fully determined at this point, but it will be. And as usual, Hassan will send out announcements through email. So hopefully we'll see you again in the fall. I'll keep the meeting room open if you would like to continue to discuss about any of the 2 talks today.
Before people start talking about physics, I think I can talk on behalf of everybody in thanking all the organizers of this fantastic series of talks. They were very illuminating, especially for me as an outsider. I enjoyed it tremendously. And I also want to thank all the speakers for such good talks. And finally, I want to apologize for bothering people with so many questions.
No problem.
Yeah.
Thank you.
Yeah, thanks. Especially thanks to Hassan and all the other organizers. It ran very smoothly. And the only point I want to contradict Nati is actually we really enjoyed your questions, Nati. So please keep them coming.
You will regret this statement, Ashwin.
I'm not the speaker, so actually I may not. Anyway, thank you.
So Maissam, there is an alternative perspective on crystalline SETs, which is this defect network construction. I was wondering if it might be a complementary viewpoint to what you're doing.
Yeah, that's a good point. I mean, it certainly occurred to us to think about that, but we have not yet thought about that. So it's definitely like on a to-do list to understand this stuff from the kinds of defect constructions that you've been talking about and others. I mean, I think that would be certainly probably very helpful because there's some of these response terms that seem kind of weird to me. I don't know how to measure them. So having, you know, a more clear understanding of where they could come from would probably be very helpful.
And for this examples, I think the defect networks will be very simple. It'll just be basically point particles arranged in a certain way.
Mm-hmm. Yeah.
Yeah, I guess people don't have additional questions.
Yeah. Okay. All right. Well,
yeah, thanks for a nice talk.
Yeah, thank you very much. Bye.
Bye.